Alright, welcome to this presentation about flexible and reusable models. This talk is called Model 10 Helicopters in a Single Model. My name is Marcus Dahl and I'm an applications engineer at Wolfram Math Core. The outline of this talk will be to first go through two different concepts called conditional components and replaceable components. I will then try to demo these concepts with sports models, and I will do a parameter sweep in the Wolfram SystemModeler link that's in Mathematica. I will then try to explain all of these concepts and why I've talked about them in a helicopter example. I will then go through a summary of my talk, and probably we will have some time for Q&A. Right, so let's begin. We will start with conditional components, and we will start with why they are important, and especially why they're important together with replaceable components. These are components that only exist if some condition is true. In this first line of Modelica code, I've defined a parameter that's a boolean, I named it resistor, and I've set it to true. In the second line, I define a component from the Modelica standard library that's a resistor. I name it resistor, and I add an if statement that says if use resistor. It means that this resistor I've just declared will only exist if the boolean use resistor is equal to true. Using this concept, it's very easy to test scenarios using the same model. You just activate or deactivate components. Like in this example, conditional resistor, I have 3 resistors in series. I have a sine voltage source and ground. I also have a 4th resistor that's right now it's deactivated. Let's see what that looks like in the text view. So this resistor R4 is defined at the end of the text view before equations, and it's controlled by this parameter boolean use more resistors that's right now equal to false. You can see it in the use if more resistor statement after declaration of this resistor. We can activate this resistor by turning the boolean to true instead of false, and we have a resistor in parallel. Set it to false, it will not exist, and the connection lines to it will also be as if they were not there. So it's a really easy concept to activate and try different scenarios using the same model. So let's move on to replaceable components instead, and why you should use them. So the good thing about replaceable component is that you can use one model and replace components instead of using different models. Selecting from a list of pre-configured options is a lot more user-friendly and less error-prone than doing it yourself in the text view. So in the left example, I have a golf bag that I've made replaceable. So I can right-click on it, go to redeclare, and then I can choose from a number of options. In this case, it will be golf clubs. In my right example, I can redeclare sport model to be either a soccer model or a golf model. So that's a bit more advanced usage. So the question is, how does it really work? How can I configure these options, and what happens when I redeclare components? Well, it's possible to declare different choices for the replaceable components, but it's not necessary. So the choices will be the drop-down menu as you saw on the previous slide. In this example, I define a base class, and in it I define a replaceable resistor, and in the annotation of this resistor I define choices, and the choices that I've defined are to redeclare of the resistors that will say R is equal to 5 or R is equal to 10, and that means we will set the resistance of the resistor to 5 or 10 ohms. I will then go and end this base class example. I will go to the example model. In this model, I will extend the base class. So now we have all the text from the base class in this example model, and I can redeclare this model in this context. So if I right click on it, I will choose r is equal to 10 and it will redefine the model. So let's first see. This is the example model. We have no resistance defined if we look at the parameters. In the text view we have extends the replaceable redeclare base class. Let's go to that class instead. If we go to that class, we can see that we have no resistance defined, and we have declared, as I showed you on the slide, it's a replaceable resistor. In the annotation we have choices. In the choices I have defined two choices, both redeclare with different resistance. Alright, so if we want to use this, we should go to the example model and we will redeclare this model. Click on it. We see that the resistance is undefined right now. We go to redeclare and we can choose from r is equal to 5 and r is equal to 10. Let's choose 10 and we can see that the resistance has changed. Alright, let's move on and try to see what these concepts can actually do. We will demo them in sports models. And for starters, I will have this seemingly simple model with just a world component and a sport model component. But actually this sport model component, it contains a lot of parameters such as ball mass, ball radius and velocities. And if I right click on it, I can see that I can redeclare it from soccer to golf model. So let's begin with the soccer model and we'll see what this model can do if we simulate it. Press simulate, go to the simulation center, and we can look at the animation straight away. Open the animation window. I will attach the camera to the ball and we can see our soccer field with a goal and a ball and some arrows. These arrows actually represent forces that are being calculated throughout the model, throughout the simulation. The green one represents the drag force from the air resistance. The red one is the Magnus force due to spin and the velocity of the ball that will make it curve. And the blue one is the velocity vector. We can see that these forces will actually change during this simulation. Let's play. Right, that was a nice shot. We can also add a trace to the ball to see the trajectory it takes through the air. Notice how the forces change. Alright, so that was the soccer model. Let's take a look at the golf model also. And to do that, we just go to the same model, we right click on the sport model, and instead of choosing soccer, I'll choose golf. And we can see how the parameters will actually change to have the appropriate ball mass, ball radius, and so on. So let's go inside the sport model and see what's actually happening when I'm redeclaring this model. We have some components that will connect the ball to the world. I have a golf component here, and I have a soccer component that has a soccer ball as an icon. And if you look at this object animation parameter, we can see that this will actually control which model I'm using. Switch it to 1, that will be the soccer model. Switch it to 2, that will be the golf model. So when I redeclare on the top level, on the sport model, I will choose different ball mass and ball radius, but also this object animation tag that will change the ball dynamics. So the forces will actually be calculated slightly differently. So this is inside a golf ball. We have some forces in a ball and a golf bag model. And this is what controls the initial velocities when we shoot the ball. We can go to redeclare here and choose different clubs, and these will control parameters such as the club mass and the loft angle of the ball. Also the velocity, how hard we are striking. We choose an iron 3 here. We get some parameters, and let's try and see what this does in the model. We go to simulate again. We open its simulation center and we can go to the animation. Instead of a soccer model now, this is a golf model, so we will have a golf course. I can attach the camera again to the golf ball, zoom in on it, and we'll see that we have some animation objects, such as a golf club and a golf ball. And the same kind of forces are applied here, as in the soccer model. The green one for the air resistance, the red one for the Magnus effect from the spin of the ball, and the blue one is also here a velocity vector. And these forces will also change during the flight. If we run the simulation, we can see that all forces become smaller as the ball slows down. And sadly, we didn't really manage to make a hole-in-one. Let's trace the path of this ball. We can shoot it again, and it's easy to see the trajectory of the ball now. So it looks like we only need to hit harder. But let's try something else and try a different club. So we go inside the sport model. We go inside the golf model again. Go to the golf bag, right click on it, and we choose Eclair and a different club. The parameters will change, club mass and loft angle, and let's try and simulate it. And we will see the difference. Again, we can open the simulation, the animation window, and it looks very similar, although the drag force is actually less and the Magnus force is a bit stronger here. This is due to the loft angle of the golf club. It will cause more spin on the ball. So if we shoot it, we'll see that it goes quite high, but don't really know how to compare it to the other club. Well, let's try to add a trace to it. So we right click, we choose a different camera angle, and then we add a trace path to the ball. So let's try to compare it to the Iron 3 to see exactly what changed. So we can open two animation windows simultaneously. Let's choose the same or relatively similar camera angles so we can compare them. We add a trace path to both balls. Alright, so both balls will show their trajectory when shot. Make it a little bit bigger, and let's see what difference actually is. So the left one, the Iron 3, goes further, the Iron 9 goes higher. Well, sadly, I'm not a good golf player, so I didn't manage to get a hole-in-one. Well, let's move on. So the next concept I'm going to talk about is parameter sweep. And that's a feature that's available in the WSM link that's in Mathematica. So first of all, why should you use parameter sweep? Well, simulations will be run in parallel. It's an easy way to automate many simulations, and also it's done in Mathematica. That means that all data manipulation and plot functions can be used that are available in Mathematica. I made a fun example of this in the same corner kick model that I used. You saw the animation of it, but now I've run 300 different corner kicks at once from Mathematica. So the same model you saw, I've run this with different initial velocities to try to see what kind of velocities I need to use to be able to score a goal from the corner kick. So we add different velocities along the goal line, different velocities in the upward direction, and different velocities along the touch line. All of these combinations of velocities, where along the goal line going from 33, 34, 35 and so on, all of these combinations make up 300 different combinations of velocities, and that's what I plotted below. So we have the goal and the corner flag, and all of these trajectories are coming from the simulations that are being done simultaneously and in parallel. I've highlighted the ones that actually managed to score, that those are the trajectories in green. The other ones I've grayed out. So this is an easy and fast way to try different scenarios. Alright, so let's move on and talk about all of these concepts, how they can be used in a helicopter example. So in this example, I've combined replaceable and conditional component and parameter sweep to make analysis of my helicopter. I have a replaceable main rotor and helicopter body. You can change the number of blades or helicopter body configuration. That means in the main rotor, you can just right click on that component, go to read Eclair, and you can choose the number of blades you want to use in your model. 2, 3, or 4 blades, and that's a really handy way to configure your model or your helicopter configuration. The helicopter body, you can choose what kind of landing gear you want to use. If you would use some stabilizing wings at the tail boom, or how you want to configure your fuselage. I made use of conditional components not only in the redeclaration, but also to make it easy to change the rotor blade complexity. The rotor blades are modeled with blade elements that is, we have different points on the blade where we apply lift forces and drag forces that affect the blade. If you have a lot of these points, a lot of blade elements, it will be a really exact description of reality, or at least the physics described. If you choose less of these points, we will get a less physical accurate model, but it will be faster to calculate. So that's a really handy way to change the complexity of the model. I've made a parameter sweep over rotor blade length. So the question I ultimately want to answer is, what's the optimal blade length for a certain engine? What happens when the engine slows down and can't handle the forces from the blades? Here I've plotted different lift forces and rotational velocities of the blade. And the different lines, each line represents one blade length. So we have blade lengths going from 0.875 meters to 1.4 meters. The first plot shows lift force over time with 800 Newton meters maximum engine torque. The second plot shows the same blades, the same blade length, and now we plotted how fast the blade is spinning around in the rotor. We first start the engine and we aim to keep all the blades at a constant velocity, 125 radians per second. After 10 seconds from going from neutral pitch angles, we are starting to increase the pitch angle until the lift coefficient starts to decrease, or in other words, when the blade starts to stall. So the shortest blade going from 10 to 30 seconds, we see a constant increase in lift force and we end up at 2.4 kilonewtons. The longest blade is increasing lift force a lot faster, but it will hit a peak and then actually go down to about the same level as the shortest blade, even though the lift coefficient is actually increasing all this time for both blades. The explanation can be seen in the lower plot, where we can see that the longest blade, the yellow one, after it hit its peak at around 20 seconds, it will start to decrease in velocity. The engine are not strong enough to handle the big forces coming from the longest blade, which means that we need to decrease the velocity we have on the blade. And if you decrease velocity, that is proportional squared to the lift force. So the net effect is that we will lose lift force. We need to keep the velocity high. So in this case, I've simulated 8 different helicopter configurations at the same time. You can easily do it for many more. And you can automate simulations, try different things all the time and changing other variables, such as the chord blade length of the blade, or how heavy the helicopter is, how fuel efficient the engine is, and so on. It's a really nice and easy way to try different model configurations. Alright, so let's go to the summary. So what have we learned? We have learned that replaceable and conditional components produce models that reduce risk of end-user error, it reduces code duplication, and it reduces the number of models and components needed in a library to simulate many different scenarios. You can also use parameter sweep to parallelize simulations and make the comparison between different configurations very easy. Okay, thanks for listening.